Okay, so welcome back. This is going to be a lesson on the derivatives of trigonometric functions. A few videos ago, I introduced the derivative of the sine function and also the derivative of the cosine function. So to remind you, we talked about how the derivative of the sine function is equal to the cosine function. So here in red, we have sine of x. Here in blue, we have cosine of x. This is, of course, assuming that x is in radians. We always assume our inputs for trig functions are in radians in calculus. So the explanation I gave before was about slopes of tangent lines and sort of like that idea of like graphing the derivative of a function based on the derivative of based on that based on its graph. But I want to give today an explanation of this fact. The fact that the derivative of sine is cosine, using a more analytical approach. We're going to do a rigorous proof here. So first of all, we need to bring back some information from our study of limits. Back in section 2.3, video 8, if we're following the OpenStack book, we learned this limit here. The limit as x approaches 0, sine of x divided by x actually equal to 1. Sine of x approaches 0. As x approaches 0, denominator will also approach 0. So that's a 0 divided by 0 indeterminate form. We were able to prove that it's actually equal to 1 by using some clever geometry and like squeeze theorem. So we're going to take that fact for granted today. We're also going to take this fact, which is was not covered in that video, but this is a similar sort of limit that you can prove but basically by using this limit, you can sort of obtain this limit along with some, I think, trig identities involved. But anyway, that's another limit that we're going to take for granted today. So what we want to do is prove that the derivative of sine of x equals cosine of x. So first, begin the proof, we'll do what we always do when we want to find a derivative. We'll set up the limit of a difference quotient. I'm going to write that this is the limit as h approaches 0. Then I'm going to write sine of x plus h minus sine of x, and then all over h, like that. Okay, well, the first thing we're going to do to this is apply a trigonometric identity, which you may have forgotten from your previous semester, but it's okay. I'll remind you. In general, in this class, I'm going to be reminding you of trig identities when you need them. So this here, sine of x plus h, that is the sine of a sum of two numbers. And there's a special identity for rewriting that in terms of the sines and cosines of those individual numbers, x and h. So I'm going to rewrite that term right there, just that part. And it becomes sine of x times cosine of h plus cosine of x times sine of h. All of that, we still need to have the minus sine of x on the end, because that is that. Okay, so we still need to subtract sine of x on the end. But this entire part right here is equal to sine of x plus h via that trigonometric identity. We have all that divided by h. Okay, so that trig identity is going to get us started. Now we can use a little bit of algebra. So what I want to do is I want to, first of all, distribute the division by h. So I'm going to take this term in particular, and I'm going to pull it aside and distribute the division by h so that I have that divided by h on its own. I'll show you. We're going to have the limit as h approaches 0. So here we have cosine of x times sine of h, and then divided by h. So there's that term on its own. Now I'm plus, I want to take the other two parts, which would be this part and this part. And I'm not actually going to separate those two in the same way. I'm going to keep them together. But I want to do something slightly different. Here, I want to factor out the sine of x. Okay. So I'm going to factor out sine of x. And then what's left over is going to be the cosine h. And here, if we factor out sine of x, all that's left over is like 1, right? Because that was all we had. I guess negative 1, because we were subtracting. So we'll have cosine of h minus 1, right? So that's those two terms with sine of x factored out, and then the cosine of h minus 1 remains. Now that all of that is also divided by h still. Okay, we're getting somewhere here. You may start to see how this limit and this limit are going to become important to us in a couple of minutes here. So the next thing I'm going to do is I'm going to split the limit over these two terms. I'm going to rewrite them a little bit. So here I'm going to write cosine of x times a fraction, sine of h divided by h. You have cosine of x times that fraction. And then we're splitting this into the sum of two limits via the sum law for limits. That's the valid thing to do. And for the second term, I'm going to take the sine of x and write it on the side. Then I have this fraction, cosine of h minus 1 all over h. Now maybe you're starting to really see. Here we see the sine of h over h. That is the same in structure as sine of x over x, right? And this is the limit as x approaches 0. And here we're doing the limit as h approaches 0. So very similar scenario, okay, just with a different variable, h instead of x. Same over here, we have cosine of h minus 1 all over h. Here we have 1 minus cosine of x, almost the same. In fact, actually, I just realized I can, if I want to make them the same, you see 1 minus cosine and cosine minus 1, I can actually make them the same by doing a little bit of trickery here. If I swap the order of these two, 1 minus cosine of h, actually, I can do that as long as I also multiply by negative 1. So I'm going to accommodate that by making this plus into a minus. There we go. So I'm just going to flip that around so that this one also matches exactly the limit we had before. Okay. So, so having done that, now the next step is kind of interesting. I don't have exactly the limits I want because each of these also has another factor that's sort of in the way, right? This is a cosine of x over here and a sine of x there. But because this limit is with respect to the variable h, really, we only care about functions involving h. We want to find the behavior of this as h approaches 0. So we're controlling that h, making it approach 0. X, on the other hand, is this separate independent variable that we don't really care about. So, like, we're focused on h, not x. So here, this part, this factor, cosine of x, that may as well be a constant. As far as the limit, this limit is concerned, that cosine of x might be constant because it's like a separate variable. This is something that happens when you have functions of multiple variables. If you continue studying calculus, you'll encounter that later. If you have multiple variables that are independent of each other, when you're doing something like a limit or derivative with respect to one of them, you treat the others as if they are constant. And that's what we're doing right here. So I'm actually going to use basically the constant multiple rule for limits to kind of pull that factor out of the limit, like this. There we go. So the cosine of x was inside, now it's outside. I'm treating it like a constant multiple, okay? Because it may as well be a constant multiple as far as this limit is concerned. Same thing over here. I pull out the sine of x. And now I can finally use the limit values that we had up here. This one is equal to 1. So we're going to put 1 in there. Cosine of x times 1. And then minus this one here is equal to 0. So sine of x times 0. And the result of this, of course, just cosine of x. And that's it. That's it. So that is a proof. Let's see, we finished a proof. So let's say QED. That means quod erat demonstrandum. It means that was what I meant to, that was what I intended to so that's how you can like really rigorously show that proof, show that derivative. Now I'm not going to go through the similar sort of thing with cosine, but you can. So a very similar kind of argument can show that the derivative of cosine of x equals negative sine of x. That's, I think, where I'm going to leave it for this video. In the next video, we'll look at some of the other trig functions.